Okay, so we're not really taking derivatives so much anymore is talking about their application. Once we finish kind of our unit 4 or 4.3, we'll be ready to move kind of on from derivatives, but we're still talking about them, their application. So one thing that derivatives tell us that's really important is whether a function is increasing or decreasing. And if a function is increasing, that means it's on its way up, and you would say that the derivative is positive. That's pretty simple, right? So it's decreasing when f prime of x is less than 0. So when the first derivative is negative, that's when it's headed down. And you kind of already knew that, right? So now is the point where you have to think a little bit, okay? Let's talk about a local maximum. Everybody agreed my hands make the shape right now of a local maximum? Tell me, what would you approximate the derivative to be at the top? 0. Now, but we would also say, actually I'll just draw it here, a local maximum and a local minimum, at both those spots, you know, you have a derivative of 0. Everybody agreed? But let's look at what the derivative is here. Before it gets to 0, you would describe the derivative as positive and then negative. Everybody see that? So the local max occurs when the first derivative changes from positive to negative. So that visual you're going to want to try to keep in your head over the course of the next couple weeks, actually through the rest of the year. But we would say the max is going to happen when f prime, and this is the notation I like to use, changes from positive to negative. And a local minimum occurs when f prime changes from negative to positive. So I was a little bit hard-headed growing up, still am, but I always just said, well, it just happens when it's equal to 0. And the fact is that can be misleading to you. And I encourage you to really be careful and think about where it changes from positive, negative, and negative, positive, because there's so many exceptions to the rule. Everybody good with that? Okay. Let's flip our notes over, and we will try the first part of the first example. These are things that I gained from a first derivative test. These are things I learned from a first derivative test. Increasing, decreasing, local max, and local minimum. So let's start here. Okay. What's the first derivative? X squared minus 4. Very good. So I'm now going to look at the graph of the first derivative. Do you know what the graph of that derivative looks like? It's a parabola. It's shifted down 4. Anybody know the x-intercepts of that parabola? Plus or minus 2? Okay. It is. Oh my goodness. Wow. All right. So the definition is the function is increasing when f prime is positive. When is f prime positive? When is the function decreasing? The local maximum occurs when the first derivative changes from positive to negative. Looking at the first derivative, when does the first derivative change from positive to negative? At negative 2, right? So I'm going to write right now x equals negative 2. That's where there's a local maximum. I could actually find the value of the local maximum, couldn't I? How would I find the value of the local maximum? Would I plug it into the derivative or would I plug it into the original? The original would tell me the y value then, okay? So we'll do that later on. The local minimum occurs when the derivative changes from negative to positive, which is at x equals 2. Not too bad, right? Okay, all right. Let's flip back to the front so we can learn about the second derivative test. You don't have to draw all these. I want you to, okay, follow and see what's happening there. I'm going to draw this. You don't have to. It's kind of a difficult picture to understand. I'm going to try to help you guys the best that I can as I draw these to try to make sense of it. I do have rhyme or reason behind it, okay? All right. So what I want you to understand is what we call concave up and concave down, okay? And right now, I'm going to say that part of this graph is concave up and part of this graph is concave down. We would say concave up in a general sense, not in definition, but concave up is kind of when you have a parabola that's going up. And concave down is kind of when you have a parabola that's going down. See what I'm saying? So like right here, do you think that the graph is concave up or concave down? It is concave down right here. And then over here, do you feel like the graph is concave up or concave down? Concave up. Now, in order to understand the definition, and this is what you want to watch, I'm drawing all the derivatives. You see those? The derivatives are represented by the slopes of all these tangent lines. What do you notice is happening to the slope of all these tangent lines? They're turning from positive to, so they're actually decreasing, right? The first derivative is decreasing. It's going from positive to negative, so on and so forth. And finally, it gets the most negative at this green line, right? And then what happens with the blue lines? It starts to tip back up, right? So when you look at the red line right here, say this first red line, you say, oh, the slope is positive, right? So we would say the first derivative is positive. But the second derivative is how the red line is changing. And the red line is changing by becoming less and less, correct? And then at the green line, it switches, and the blue, although it's negative, it's becoming more and more. That's the difference between the first derivative and the second derivative. So we would call this concave down. We would call this concave up. And then the point at which it switches concavity, we call the point of inflection. So in this situation, you notice that the red lines, that the slopes are becoming more and more negative, and then finally they switch to becoming increasing, becoming positive, right? So the point of inflection is where the second derivative changes sign. So let's define these. A graph is concave up when f double prime of x is greater than 0. So whenever the second derivative is greater than 0, that's where it's concave up. It holds water, okay? It's concave down whenever f double prime of x is less than 0. A point of inflection occurs when f double prime changes from positive to negative, or f double prime changes from negative to positive. If f double prime ever changes sign, that would be a point of inflection, we call. Somebody tell me something about, sorry. Somebody tell me something about the second derivative and a local maximum. when a local maximum, if there's a local maximum, the second derivative is negative, right? So a local maximum, am I concave up or concave down? Concave down. So if there is a local maximum, then f double prime of x would be negative. And if there's a local minimum, then f double prime of x would be positive. So let's go to our true example and try to figure that piece out. Okay, we have concave up, we have concave down, and we have inflection. So I need to find the second derivative for this. Can somebody tell me if this is the first derivative, what is the second derivative? I have 2x. So I'm going to draw a graph of 2x. Somebody describe for me the graph of 2x. Line with a slope of 2 passes through. Everybody good with that? So it's concave up wherever f double prime is positive. Where is f double prime positive? 0 to infinity. It's concave down wherever f double prime is negative. Inflection occurs whenever the second derivative changes sign. Does it ever change from negative to positive or positive to negative? At 0. I'm going to write x equals 0. We could figure out the actual location of that by plugging it into the original. Those are our definitions. That's how we're defining the material. Let's try the next example. I will label increasing, decreasing, local max, local min, concave up, concave down, and inflection. All right, first derivative. Negative 4x cubed plus 4x. I would like to look at that graph. I think it's easiest to look at the graph. Is this factor? Take out negative 4x, and I'm left with minus 1. So therefore, f prime of x is equal to negative 4x times x plus 1 times x minus 1. Sometimes we can use what we call interval testing, and sometimes we can use a graph. I happen to know what this graph looks like. What values does this graph cross the x-axis? Negative 1, 0, and 1. If it's a cubic, can somebody describe the shape? Yep. So it's a negative cubic, so will it start down and finish up, or will it start up and finish down? Start up and finish down. So I'm going to start up, and I will finish down. If you could draw the graph, draw the graph. That will make it easiest. If you can't draw the graph, then go ahead and use an interval testing method, which I'll show you later on. Okay, that's my first derivative. Intervals of increasing. That'll be wherever the first derivative is positive. Yep, negative infinity and negative 1 right there. And then, as you said, we have 0 to 1. Decreasing wherever the first derivative is negative. Notice that these are intervals. I'm going to actually find a coordinate here, okay? A local maximum happens when it changes from what to what? When the first derivative changes from positive to negative. Is there a time it changes from positive to negative? Happens twice, doesn't it? It happens at negative 1 and it happens at positive 1. Happens at negative 1 and it happens at positive 1. So I'm going to plug negative 1 into the original function so I can actually find the location, the y value. See what I'm saying? If we plug in negative 1, negative 1 to the fourth is 1. Make it negative, negative 1. And it would be plus 2. So I'd have a height of 1. And if I were to plug in 1, does everybody see I'll come up with the same result? The local minimum occurs when f prime changes from positive to negative, or from negative to positive. When does that happen? At 0. Changes from negative to positive. So if I plug that back in the original, what value do I get? 0. All right, in order to determine these other three, what do I have yet to do? Take the second derivative, correct? So let's take that second derivative. Can somebody tell me what the second derivative is, as I can't see it now? Shape, parabola, upside down. Could we find where this crosses the x-axis? Yeah, I'm wondering where does, I'm going to use some space over here. Where does negative 12x squared plus 4, where does that equal 0? You would solve that by subtracting 4. Negative 12x squared is equal to negative 4. Divide by negative 12, x squared is equal to 1/3. Square root both sides. X is equal to plus or minus. What's the square root of the top? 1. The square root of the bottom is the root of 3. Can I leave my result like that? Nope. Root of 3 over 3. Thank you. So it's a parabola that's upside down and it crosses through two spots. Negative root of 3 over 3 and positive root of 3 over 3. So I have my second derivative. Where would I then be concave up? Negative root of 3 over 3 to root of 3 over 3. Wherever the second derivative is positive, which is that region right there. My original function is concave down at the other location. So from negative infinity to negative root of 3 over 3. Union root of 3 over 3 to infinity. Inflection happens when the second derivative changes sign. Does the second derivative ever change sign? Change from negative to positive. I change from positive to negative. So we're going to have 2 points of inflection. One would be negative root of 3 over 3. The other one would be root of 3 over 3. I would like to figure out y value, so I'm going to plug that into my original equation, and I'm going to need my calculator for that one. Usually once a year, I have a can't use your calculator on a test. You won't have that situation this year, okay? But this is usually a good one to have that. The problem is, as a teacher, you got to figure out how to not end up with those values. But we'll plug it in. I go to my original function, and I have, is it negative x to the fourth plus 2x squared? Agreed? Okay. And I'm going to go into my table of values here, and I'm going to type in negative root of 3. Notice how I'm going to close my parenthesis around it and then divide that by 3. And I get 0.55. And then I will type in positive root of 3 divided by 3. And again, I get positive 0.55. Notice that the root of 3 over 3 is like 0.57. Okay. And I'm going to do one last thing here, and then you guys can start practicing a couple problems here within your assignment. But the key is, what will this lead us to? And our ultimate goal, which you could kind of now do at this point, is to sketch an extremely accurate graph of this. And what I want to show you is what we know at this point. I know that this graph goes through a location of 0, 0. Everybody agreed? And I know it has a local max at negative 1, 1. I know it has a local max also at 1, 1. I also know that if you consider its inflection points, those happen at negative 0.57 and 0.55, which would be about right there. And then positive 0.57 and 0.55, which would be about right there. So I currently have 5 points on this graph. It's a 4th degree and it's negative, so it could be right side up or upside down. Upside down. Now the last thing that we could determine from this, if you wanted to, is you could actually find these x-intercepts by factoring out a negative x squared. You would get an x squared minus 2. So if I have x squared minus 2, everybody agrees it would cross at positive root of 2 and negative root of 2, which is about 1.4 and negative 1.4. That adds some more points for me. So here's the big idea that I want to show you guys, which I think is just really super cool. If I take that graph, you guys always ask before, how high or how low do we go with that situation? I'm going to take my window and I'm going to make it a negative 3 by 3 and another negative 3 by 3. And if I check my graph, it's pretty much dead on. So think about all the years where people did not have a graphing utility. How could they come up with the accuracy of a graph? And some people might be like, oh, that's just a general sketch. I don't think this is just a general sketch. I think that's pretty much the real deal. So perfect polynomial, graph perfectly, right there, checked by my calculator. That's our ultimate goal, is to be able to do the whole thing. Take out your assignment. Please look at problems 1 and 2 and 3. What I would like you to do today is to be able to look at problems 1 and 2. You'll be able to identify the increasing, decreasing, concavity, min-max, inflection, all that stuff. And then in problem 3, you do it again. But then take your results and try to sketch a graph. Okay, that will lead you in what we do in a lesson when you guys return from a Thanksgiving break. The next 2 problems you are not ready to do yet. That's what we'll have to cover tomorrow in order to prepare you for that. So go ahead, take some time, see if you can come up with these initial intervals and points for increasing, decreasing, so on and so forth.